Dr. Craig Edward DeForest is an American heliophysicist and the former chair of the American Astronomical Society's Solar Physics Division. He is now the director of the Department of Solar and Heliospheric Physics at the Southwest Research Institute's Boulder, Colorado offices. His wide-ranging contributions to the field of experimental astrophysics of the Sun include early work on the MSSTA, a sounding rocket that prototyped modern normal-incidence EUV optics such as are used on the Solar Dynamics Observatory. His discovery of sound waves in the solar corona in 1998. Standardization of computer vision techniques that are used to measure and track magnetic fields on the solar surface. Co-invention with colleague Charles Kankelborg of the fluxon semi-Lagrangian approach to numerical MHD modeling. And pioneering work on quantitative remote sensing of the solar wind via Thomson scattered light. Dr. DeForest is noted outside the heliophysics science community for his contributions to open-source software, particularly PDL and Audacity, and for his extensive work on science outreach to the public. Dr. DeForest is the principal investigator of the PUNCH mission, which launched in 2025 to study the solar corona and the origin of the solar wind.
I'm going to take you on a little zoom, out from, if you're right now on site, you're at Regis, and it's important, especially with solar physics, to really capture a sense of the scale of the things you're looking at, right? We all spend a lot of time imagining what it's like to compare size of things to a galaxy or a supernova, and these are very hard, mind-bending things. But the sun is small enough that its immensity actually hits home. So here we are. This is this field of view is about a mile across, 0.8 miles across the arrows there. There's Claver Hall at Regis. We're going to zoom out a little bit. 80 miles is about the distance from CU Boulder down to the Air Force Academy in Colorado Springs. And you're right somewhere in the middle if you're on site, or all over the country if you're not. You can drive that in a couple of hours, right? In an hour if you're a speed demon and it's the middle of the night. If we zoom out another order of magnitude, you're up to about 800 miles, that'll take you from the tip of California down into Mexico, or alternatively, it'll take you from the middle of Wyoming, say Casper, down to Las Cruces, New Mexico. So that's about the length of a college road trip. Raise your hand if I can see you. Hey, that's neat. Raise your hand if you've ever been on a college road trip that was at least 800 miles, right? Most of us have done that at least once in our lives. So you can drive that in one grueling day or two relaxed days, or fly it in a couple of hours. Zooming out a little more, also 800 miles. I like to use Texas as a reference because it's one state and it's almost exactly 800 miles tip to stem to stern. So from the northern corner there with New Mexico down to Starbase or whatever down below Corpus Christi is 800 miles. And so that's again sort of a college road trip. If we zoom out a little bit, we can place that in context on the sun. So this is real solar data you're looking at now through a solar filter and a 1 meter telescope. And what you're seeing is convection cells on the surface of the star. They're about the size of Texas. And just for a sense of the temporal scale and the violence that a star carries out, these convective cells rise, spread out, cool off by emitting sunlight, and sink in about 5 minutes. That's about how long it takes. And they're about the size of Texas. So if you can imagine that, and then zoom out a little more, it's happening all over the sun all the time. There's about 1 million of those granules all over the surface of the sun. That giant hole is a sunspot. We were just hearing about sunspots. There are some large naked eye ones on the sun now. We're in late phase of the solar cycle, and so the sunspots tend to be larger and produce stronger flares and CMEs coming out. The sunspot is an area, it's not a void going down into the the star all the way, but it is a depression. It's caused by the magnetic field of the sun. It's concentrated right there, that prevents the lateral motion of those convective cells, the granules, which causes the surface to cool off. And of course, you can see what's called the penumbra around it. Looks like the iris of an eye, this area out here, which is formed by the magnetic field leaning over sideways and stretching out the material on the way as the field exits the surface. So we had Texas. Now we can draw the entire world to scale, and that's sort of the size of a typical sunspot. About everybody here knows it's 1% of the way across the sun is the diameter of the Earth. So about 1 million Earths could fit inside the sun if you squished them all flat, or squished them all so that there weren't any gaps between them. That's about 8,000 miles across. So that's 10 college road trips. We're still on a human scale. 8,000 miles is not that far, right? That's the distance between oil changes. It's how far I personally drive in about 6 months, right? I put about 15,000 miles on my car in a year. If you commute, you probably do too. Zooming out a little more, this sunspot is not so recent. This one is from last spring, but there it is next to the Earth. And you can see little bits of the granulation all over. We're now looking at 250,000 miles, which is pretty far. That's as far as my old VW van drove before it finally rusted out. It was on its third engine at that time. So again, 250,000 miles is not that far. Somebody who's a frequent flyer might fly that in a lifetime. And of course, a long distance trucker might drive that in a lifetime. If we continue zooming out, the sun's about 800,000 miles across. That's about the distance that a long haul trucker would drive in an entire career. And that's the size of the star. So again, this is a human scale. Although the sun is much bigger than the Earth, it is not so large that we can't comprehend the distances involved. And that's important because we're about to zoom out even more. We can zoom out a little bit and start looking at the corona of the sun. The surface of the sun is at about 6,000 centigrade, 6,000 Kelvin, 10,000 Fahrenheit. The atmosphere of the sun is mysteriously much, much hotter. You probably know that. Have you been to see an eclipse? Again, raise your hand if you've seen an eclipse. We've had several. Right on. Excellent. Okay, that is the hottest material you're ever likely to see in your lifetime. And I sincerely hope it's the hottest material you ever see, because the only other thing you're likely to see that's that hot is a thermonuclear explosion. That material is 1 to 2 million degrees C. And you can see it with the naked eye right there in the sky during an eclipse. Here you're seeing it in extreme ultraviolet, which doesn't penetrate the atmosphere, so you have to go to space to see it, even with an instrument. But in this wavelength band, the surface of the sun is dark. It's just not hot enough to glow at these temperatures. So we can see the ultra-hot corona over it. Here you can see that above every sunspot is what we call an active region. That's an area where the field, the magnetic field, is producing extra heat. And so you get these highly dense and hot regions in the corona. I see a hand up. Dr. Morrow.
Oh, Dr. DeForest, I was responding to that I'd seen an eclipse.
Aha, excellent. Perfect. All right. So let's zoom out a little more. Now we're at 5 million miles. That's about as far as even the most frequent flyers, airline pilots, might fly in a lifetime. And here, now you're looking at what you can see with the naked eye during an eclipse. You can see the moon blocking out the sun. You can see a red region around here. That's emission from hydrogen in the chromosphere of the sun, so-called because it is colored. And then above that, you can see Thomson scattered sunlight. That is sunlight that's been scattered off of free electrons in the space around the sun itself. So the corona that ghostly white apparition that we see during an eclipse is electrons. It's mixed in, sure, with ions that neutralize it, but what's reflecting the sunlight is the electrons. So if, like me, you ever as a kid wondered what an electron looked like, well, that's it. Well, that's a lot of them. So this was taken, the 23 eclipse by Starha, Habal, and Druckmüller. Druckmüller's sort of famous for enhancing the contrast in these images, so they just look so stunning. The reason the corona is structured like this, of course, is the same magnetic field that causes sunspots. The material is hot, so it's ionized. There's a force on each particle that's perpendicular to the field and the direction of motion that causes the particles to spiral around magnetic field lines. If you stand back 100 million miles and squint a little bit, that spiral looks a lot like a straight line. And so what we find is that the particles are semi-confined on a particular field line or set of field lines. And so they trace out the shape of the magnetic field in the corona. What you're seeing here is a combination of the field bending over and being pulled outward by the acceleration of the solar wind itself out of the corona. The material is so hot, it's not gravitationally bound. And so it streams out and becomes a tenuous wind in outer space. Moving farther, 15 million miles, we can see that the sun's corona doesn't stop at the edge of an eclipse. It keeps going out. And so here, this field of view is 15 million miles across. It subtends about 12 degrees on the sky. And so it's about the size of your fist extended at arm's length. You can see that the corona extends quite far out. This is the deepest field movie of the solar corona ever made. It was made from space so that the atmosphere couldn't interfere, and heavily processed in order to reduce the noise level and reveal all this ghostly stuff leaving in all directions all the time. And that's 15 million miles, but that doesn't end there. We can go a little farther out. We're now 35 million miles out, looking at the corona on a quiet day. What I want you to see is this is the end of the corona. If you have kids, by the time they're 5 years old, they know how to draw the sun. They draw a circle, they draw radial lines coming out from it, right? How many of you have drawn the sun that way? I know I did when I was a kid. My parents have proof. Well, now we know, A, they're right, that in fact the corona does have radial lines in it, and B, we know how long those lines have to be. They have to come out to about here. What you're seeing here is a fundamental change in the physics away from the sun. As this material moves out, the gas dynamics of the material become more important than the magnetic physics that's confining the material laterally down here. So down close to the sun, the magnetic field laterally confines the material, prevents it from spreading sideways, and you get these radial structures coming out. Out here, about 80 solar radii, 50 to 80 radii away from the sun, the gas dynamics start to dominate, and these streams break up, just like the stream from a squirt gun, for almost the same reason. They break up because of the onset of turbulence, that there are vortices and eddies forming here that break up those radial lines. Now, it's very hard to see this type of movie because the material here is getting much fainter than the star field. At the right-hand side of the image here, you can see the material against the star field, but on the left-hand side, it's 100 times fainter than the background stars. And so it requires some significant image processing to drill down that far into the images. Now, that was a quiet day. On a not so quiet day, this is what the same field looks like. What you're seeing here is a coronal mass ejection. It's many times larger than the star itself. And it's a moiling, churning mass of unstable magnetic field and the material that's caught up in that field, erupting across the solar system at about 1 million miles an hour, 1 to 4 million miles an hour. You can see that these events are very structured and extremely rich in detail, and there's quite a bit of physics going on in the evolution of the interior. However, they're hard to see just because they're so faint compared to the background stars, but they are there. This field of view, again, is about as large as your fist extended at, it's larger than your fist extended at arm's length. But it doesn't stop there. The solar wind is visible all the way out. It's visible so far out, we can't fit everything on one screen. So I had to change the coordinate system. We're going to look at the sun here in the extreme ultraviolet and zoom out. And then once we're out far enough, we'll change to polar coordinates so that you can see everything all at once. There's Venus and the Earth to scale 90 degrees away from the sun. We're going to polar coordinates now. So horizontal lines are radial to the sun. Now in this coordinate system, we've got a logarithmic scale on the x-axis. So this was a movie that was taken by the Stereo spacecraft quite some time ago. Stereo, you may know, is in solar orbit. And so on the way away from the Earth, orbiting the sun, it turned to look back toward the Earth and the sun and captured some of these coronal mass ejections, leaving the sun and crossing the void between the planets. So over on the right here, you can see a vertical bright line in the blue section. That is the round limb of the sun. And then this in the extreme ultraviolet. And then the orange and the white areas are visible light. So this orange area here is the corona that you would see during an eclipse. And then out here is the very tenuous solar wind revealed against the background of stars that are up to 1,000 times brighter. So what I want you to see is the formation of a knot of material here. The movie will loop around in just a moment. That knot of material forms in the atmosphere of the star and gets ejected out through the corona, sweeps across the solar system. Here it comes. Get ready. It's forming. There. Gets ejected, crosses through the void, sweeps over Venus, which happened to be in near conjunction with the Earth, or conjunction with the sun, and then sweeps over the Earth itself. When it hits this gauge pegs, this gauge is calibrated in density as measured by a probe sitting right in front of the Earth. So this is an example of material in the star and processes happening in the atmosphere of the star directly affecting our planet. We live here. All right, moving forward. What I'm really talking about at the end of this, for the last part of this talk, last 2/3 of it, is a mission called Punch that I lead that we just launched. Now, Punch is the polarimeter, that's a polarizing camera, to unify the corona and heliosphere. That's to produce a joint understanding of the sun's corona, the atmosphere of a star, and what you might think of is the empty space between planets, which is far from empty, as you can see all this material moving through it. So on the left here, it also unifies two fields of science. On the left, you can see a coronal movie. This field of view is about the size of Orion. You can see the stars going by in the background and various coronal mass ejections shooting out from the sun. This typifies how we study the sun by remote sensing. We use telescopes and spectrographs and things to look at the star from afar. Over on the right, this is how we study the solar wind. And traditionally, for at least 70 years, or 60 years, we have sampled the solar wind. We send a spacecraft out with probe instrumentation on it that samples the magnetic field. That's this bottom trace down here, the temperature of the plasma, the density of the plasma, and the speed of the plasma, and other parameters, all as a function of time as that material sweeps over the probe. So right now, we're in the process of bringing that process or that type of study into the corona. That tells us everything there is to know about the plasma at a single location, the location of the probe, Parker's Solar Probe at great expense is flying down into the corona and sampling it periodically. It's wonderful. I'm at a meeting here to celebrate that and learn about the most recent results. Punch goes the other way. I like to say if all you have is an in situ probe to study the solar wind, that's like trying to study human anatomy if all you have is an electron microscope. Right? The electron microscope will tell you everything about how a particular cell works or even a structure in that cell, but it won't tell you much about how a tendon connects to a bone or to how your bones are connected to articulate and make your joints work. And so Punch brings the large and mid-scale physics or measurement of the sun out into the solar wind. We have 4 spacecraft. They are currently in sun-synchronous orbit. I'll talk about that a little bit. They are orbiting over the day-night terminator line, and they're using the oblateness of the Earth to perturb the orbit. As we orbit the sun, the terminator goes around once per year, and so the orbit also has to precess. We're in a very carefully tuned orbit that keeps us always right over that dawn-dusk line so that we're always in the sun. Why do we have 4 spacecraft? Well, the first thing is we have 1 that looks close to the sun and 3 that look farther away. There's just too much dynamic range in the field. The other reason is the field of view is too big. It's so large that the planet gets in the way. Here's an example of the Punch field of view with the 4 spacecraft fields all superposed on a familiar object. Here's an eclipse happening over a suburban neighborhood back in 2017. One of our co-investigators took this picture. The field of view is enormous. It's 90 degrees across. And so we couldn't fit it into the region around the Earth. We had to make our instrument, or a virtual instrument, that's as large as the Earth so that we can look out in all directions at once. So this is what our field of view looks like in space. It's 200 million miles across, 2 AU across. And we're imaging the corona at the very center here, and then the solar wind farther out. This is a simulation of a coronal mass ejection crossing the solar system. And by spreading out around the Earth, we ensure that every direction we want to look is up, right? Up is in different directions in different places. And so we take images simultaneously with all 4 spacecraft and merge them on the ground. And that gives us this continuous view. Let's see. So we can look in as far as 6 solar radii, out as far as 30, and then we have mosaic images that are combined from all 4 spacecraft that give us an image every 4 minutes out to 80 solar radii. That's about 10 degrees away from the sun in all directions. So as large across as 2 fists held at arm's length. Our outer limit is 180 solar radii, 45 degrees away from the sun. This is how we deployed. This movie was made a long time ago. We actually have launched since then, and we didn't, the booster didn't look like this, but the deployment sequence is the same. We ejected our spacecraft in orbit at about 1 meter per second. That's a walking pace away from the launch vehicle, and they just drifted apart. Less than an hour after launch, they deployed their solar arrays, and then they just continued drifting. Now, if you started walking right now and you just didn't stop, in about 90 days, you'd get 1/3 of the way around the world. And so they're doing that. They're drifting apart at about 1 degree per day. 30 days after launch, which was about a month ago now, or 3 weeks ago, we opened the doors on the instruments. And that allowed us to get first light and photograph the corona and the star field around the instruments. We've been continuing to check out the instruments. And in about a week or 2, we will start collecting joint data with all 4 instruments so that we can test them out as a constellation. About 100 days after launch, we fire a tiny rocket engine, you just saw that in the movie, to arrest the drift rate And then thereafter, we just continue rolling every 30 degrees or so of orbit to keep the Earth underneath the baffles of the wide field imagers. And that allows us to see the star field out in space. And so those fields of view, if you turned the other way to face off to your right over your right shoulder, you would see that field of view pattern in your mind's eye. That is how we operate. I'm going to go back and just remind you what those fields of view look like. Whoops, here, one more. There is like that on the night sky. Okay, why polarization? We use polarization because the light that you see from the corona and the solar wind contains information in the polarization signal about 3 dimensions. So we have a problem when we try to forecast the arrival of CMEs and aurora at Earth, geomagnetic storms. The problem is this: we predict them by looking at the corona. There's a CME coming straight at you. It looks, if you're of a certain age, which I am, you remember the Romulans fire a weapon at them, and it looks uncannily like this CME coming straight at you, which is odd, since we didn't know about CMEs for 20 years after Star Trek was filmed, or for 15 years. So there it is. The problem is we can't tell the difference between a wide, slow-moving CME or a narrow, fast-moving CME. The fast one will arrive more quickly and also carries a lot more kinetic energy, so it will affect the Earth more. Using polarization, we can tell which is which. How do we do that? Well, remember, polarized sunglasses work the same way as our polarizers. They emit light whose electric field is oscillating in one direction, in this case vertically. So if you take a pair of sunglasses out to the sky and you rotate them, you'll see that the sky itself is polarized. Rayleigh scattering in the atmosphere polarizes light. Well, Thomson scattering, which is the process by which electrons scatter light, works almost the same way and does polarize the light. So we use the difference in brightness from different polarization angles or polarizer angles to find out what's going on in 3D. The reason for that is, say you're an observer, there's the sun, you're looking at an object that has some elongation angle that we call epsilon. Well, it also has to scatter sunlight through this angle chi, the scattering angle. And when it does, it polarizes the light to a degree that depends on chi. So if we measure the degree of polarization of an object out in the sky, the amount of polarization in that light tells us chi, which allows us to solve this triangle. If you think back to your high school geometry class, you know this angle, therefore you know this angle. If you know 2 angles and one side, the sun-Earth distance, you know the whole triangle. So that's what we do. That's why we're a polarimeter. I'm going to show you some baby pictures. This is the narrow field imager. It's a coronagraph. When this door opened, I can say opened in the past tense now, it revealed a dark opening, or a dark room in front with an occulter that blocks out the sun itself and the optics in the back. So this is NFI or NIFI undergoing stray light testing before it was delivered. That's what it looks like in normal room light. You can see there's dark interior space and a shiny metal occulter that blocks the sunlight. Here's our wide field imager. That's a flat box. When this door opened, it revealed some deep baffles to absorb moonlight and other glint, some solar baffles on the front, and in the very back, a little lens system that images the sun. This is what it looks like on a test stand. Now, to give you a sense of why we went to this extreme with these crazy looking baffles, we attenuate sunlight by 16 orders of magnitude. 16. That's one with 16 zeros after it. Here's a picture through the instrument itself of the inside of a vacuum chamber. Why is it in a vacuum chamber? Well, we're not worried whether it can survive in the vacuum of space. We can't test it in air. Air has Rayleigh scattering. The sky is blue. And it turns out on an object of this scale, if we shine light across the top, the air over the top of the instrument will scatter light down into it at the 10 to the minus 11 level. So we had to be 5 orders of magnitude darker than air in order to test this thing. So here's a picture of the baffle itself as seen from inside the optics. And then these are some features in the vacuum chamber. And we were demonstrating with this image 10 to the minus 16 performance in stray light. The optics in the wide field camera, folks who are astronomers, you, will be interested. We use basically an eyepiece. Remember, ray optics work in 2 directions. You can use an eyepiece to bring a small real image from your main telescope out to infinity so your eye can see it comfortably. Or you can turn that eyepiece around and bring objects from infinity on the night sky down to a real image with the same optics. Al Nagler designed the Nagler eyepiece for Teleview, and we hired him to design the optics for the wide field imager. So here's a picture of me with Al Nagler at our site visit when we were proposing the mission. So these optics being designed by Al are really great. They have a wide field of view and really excellent resolution all the way out to the limit of the field of view and beyond. Really pleased with them. This is the first image we took through those optics with the actual spacecraft. The spacecraft was sitting on a test stand in a clean room, and those are the people who built it. And we told it to take a picture, and there it is. So that's the laboratory at Southwest Research Institute where the picture was taken. Now, this haze is not real. They're in a clean room, so there's no haze. This is because of the way we read out the camera. The camera was designed to operate very cold. We can't cool it enough to operate in its normal configuration in air, because all the moisture would condense onto the chip. So we were running it warm, and that gives this hazy effect. These are images of the spacecraft themselves in packing cases arriving at Vandenberg Space Force Base last February. This is what they looked like after we unpacked them and put them in little space frames to undergo testing and integration with the rocket. They're in a clean room right there. There's some people in the background. This is 8020 aluminum, if you've ever used that. These things are about 1 meter long. This is the same spacecraft now mounted to a launch vehicle. There's another mission called SphereX on top of them, and those are the punch spacecraft bolted to the side. We put them inside a giant fairing and put them on top of a Falcon 9 and blasted them into space. So it happened. This is what they looked like in the clean room during integration with the fairing. There's 2 out of the 3 wide field imagers right there. And over on the right, that's the narrow field imager, the coronagraph. And they're bolted and spring loaded on these little side ports that are designed for rideshare payloads, which we were. Let's see. These are images taken with a live video feed from the launch vehicle as NIFI and then the WIFIs deployed. And that's how fast they left the spacecraft. That's the coast of Africa you see under the spacecraft. These are 2 different cameras, by the way. The one on the left is looking forward. Sorry, is looking backward, so you can see the Earth coming by. The one on the right is looking forward. This is where the spacecraft are now. Today is day 56 of the mission. We've been in space 56 days, and they've drifted apart. So they're each of the WIFIs, the wide field imagers, is separated by about 50 degrees in latitude. This image came from n2yo.com, which lets you use the NORAD orbital data tracking to track any satellite. Many of you know, but many of you probably don't. NORAD, the same people who are charged with defending us from a missile attack from the Russians, track every single object orbiting the Earth. There's a radar curtain extending up over the pole and another one in Colorado that is brighter than the entire galaxy in that one narrow band of radio. And it tracks everything that they can, and they publish every track. They do that because it's in everyone's best interest that nobody gets nervous when they see something coming at them in space. So everything that NORAD knows about gets tracked. You can track it on this website, including Punch. This is our first light image through Punch. That looks nothing like the sun. What the heck? No, this is normal. What you're seeing here is this dark feature in the very center is the occulter. You're looking out at the occulter. This bright ring here is sunlight that's being diffracted around the occulter. And it's being attenuated by 9 orders of magnitude. This haze here is stray light in the instrument. That's typical of a coronagraph. There's a little more in NIFI than we expected, but it's not enough to damage the science. And then out here, there's a region of less stray light, and then out here, the dark areas are outside of our field of view. When we process this image, I just did a simple unsharp mask. We can get rid of the smooth stuff and reveal the star field. And we can see that, in fact, this instrument is in excellent focus. And the data will be very scientifically useful. However, we have to process them to remove the stray light. That is fine, and it meets requirements and is within our expectations when we set out to design the instrument. It's just in the nature of coronagraphs. These green lines here are tracing out Pisces. Some of you may recognize that particular angle. This is our first light image from the wide field imager. This imager had essentially 0 stray light. Right in the corner here, you see a tiny little glint off the edge of the baffle that's coming from the Earth underneath the instrument. But there's essentially no stray light inside the instrument itself. All of this haze is the zodiacal light. We also call it the F corona. The zodiacal light, if you've all seen the zodiacal light, right? Who here has seen the zodiacal light? Yeah? Yeah, okay, a few people. So we live in a dust cloud. Dust is orbiting the sun, micrometeorites, usually on the scale of a few microns, but down to submicron levels. And it scatters light. So on a very dark night, you can see a slanted sort of column of light coming off the horizon. It looks very much like this. In this case, the horizon is our baffle, and we're in outer space, so the sky is even darker than on the Earth. But anyway, that's what it is. You can see some constellations here. You can see the Pleiades and the Hyades photobombing as usual. An Iris here is an asteroid that's 9th magnitude. We just saw that in the first light image. Really nice. This is our first overlay showing how the data will fit together. We just did this manually, but you can see, for example, the tip of Pisces is not in the coronagraph field of view. It is in the wide field imager field of view. And they all line up very nicely. So moving forward, we have 3 wide field imagers. Here's the first light from another one. It looks very much like the first one. That's fine. Here's the second one, or the third one, WIFI 3. Here's the Pleiades again, slightly different position. What's that out of focus thing over on the right? Well, we'll follow in the footsteps of Messier himself. Zoom in a little bit. Oh, that's baby's first galaxy. That's the Andromeda Galaxy. The instrument here has about the same acuity as your eye. So that's what you could see if you had almost perfect night vision. You can't, but you can see at least the core of it as a slightly out of focus object. We were talking before the meeting kicked off. If you bring supplemental oxygen, that improves your night vision. So especially if you live at altitude or observing up in the mountains where the sky is dark, bring a can of oxygen and have a look after taking a whiff of that, and you'll see more stars. It's true. Yeah. We are not just a camera, we are a polarizer. And so this is our first polarized image. again, the Pleiades and the Hyades here, showing that the zodiacal light is in fact polarized. We're using a method called the tripolarizer method for measuring linear polarization, and we've encoded this image so that the hue tells you the direction of polarization, and the saturation tells you how polarized the light is. So down here where it's white, that's not very polarized. Out here where the colors are more intense, it's more polarized. And this is following published values for just how polarized the light is coming off of those little dust particles. So pretty nice to see that, yes, in fact, our polarizers work right. The other day, we took a picture of the Smiley conjunction. We're just testing out the instrument, so running it through its paces and looking at various objects that will interfere with the science we want to do. In this case, the moon and Venus and Saturn, and Neptune and Mercury. So that's 4 planets plus the moon, 5 if you count the Earth, which I guess you can't because it's just a little glint here. 4 planets plus the moon all in one image. The moon is so bright that, and in fact, all these planets are, that they saturate a pixel on the detector and also wash electric charge across the surface of the detector itself. That makes these bright white artifacts around very bright things. But totally harmless, just looks weird. This is a picture we took last weekend during the new moon. We wanted to see if the moon itself would swamp or otherwise interfere with the coronagraph images from NIFI. So we continued taking data during the new moon, and there's the moon. That is a new moon, as seen with NIFI. How many of you recognize a new moon? Right. It looks like a full moon. The reason it looks that way is it's lit up by Earth light, right? If you were on the surface of the moon at the new moon, you would be experiencing a full Earth, and so it would be brightly lit. And we have a very sensitive camera, so we're imaging what looks like the full moon, even though it's only lit by Earth light. So sort of neat. So punch data are coming. You can analyze punch data. They're available to everyone for any purpose. We have links to get to them on our website, which you can copy down or Google us, Punch Mission. And this week, we plan to start pushing data. It may be a week from today, or it may be as soon as Friday. And you too can analyze and look for what's odd about that image. We do a lot to our data, a lot more than most missions ever do. For example, we use not linear flat fielding, but quartic polynomial flat fielding on our detectors. And we have to put the data through a lot of steps in order to first preserve their photometry while calibrating them. Second, turn them into mosaics, so we have one virtual instrument. And third, background subtract that virtual instrument so that 99.9% of the light in the image is removed, leaving the 0.1% that we really want to see. So there's a lot to it. One of the problems we face, just as an example, in combining these things into mosaics is we have coma, just like you do. Everybody has coma. Everybody who uses a telescope. In fact, we did a literature search, and it turns out the first reference we could find to people complaining about coma in their optics was 2 guys named Galilei and Kepler, who wrote together in 1611 and groused about how these brand new telescope things that Galilei had started deploying smeared out the stars near the edge of the field of view. Go figure. It's been a problem for a long time. We post-process every image and digitally remove the coma. We can do that photometrically. We published papers on the subject. So that's a solved problem. But I want to show just why we have to go to such lengths and why our pipeline is so complicated. So I'm going to take you on a little tour into the data from the stereo mission. Remember a while ago, I talked about stereo looking back that produced that Sun to Earth movie that we showed toward the beginning of the talk. This is a tour through the stereo data and what we had to do to make that movie. So here you see a star field with Venus and a vertical stripe because it's so bright, and the Earth itself with a vertical stripe because it's so bright. Over here on the left, you see a little piece of metal in the camera that was designed to block out the Earth so that it wouldn't do what it's doing right now. But it didn't quite work. You can see the zodiacal light. Stereo is orbiting the sun. And if you're careful, you might recognize Pisces right in here. So let's see. The one last thing is this color bar is 0 to 30. These are 2-hour exposures you're looking at. Each one is 2 hours. And these are the color bars in counts per second. So each pixel received 30 counts per second if it's white, 30 counts or more per second if it's white. And shades of gray, 5, 10, 20, whatever. Okay, now keep an eye on that because we're gonna do some stuff. All right, there's Earth, there's Venus. All right, the first thing we do is we treat each pixel in the movie as a time series, and we just subtract the minimum value of that pixel. That way we can see features above the background. And when we do that, the first thing is you see a lot more stars. That's because we compress the dynamic range. Instead of 0 to 30, it's now 0 to 1. There's a lot of stars in there. You can also see a little halo around the planets from scattering in the optics. You can see something interesting going over on the right, but it's hard to see against the stars. So let's get rid of the stars. We can resample the image so that the stars are fixed. Having done that, we can use the same trick. We can subtract the minimum value of each pixel in this coordinate system. There's Uranus right there. See, the stars are fixed, but the planets move. If you look carefully, you'll see Uranus. It jumps at the end. Boom. So we can subtract the minimum value. We get this. Now we're from 0 to 0.1. Okay, so a factor of 300 inside the original data. We can see all kinds of weirdnesses here. We can see that the zodiacal light, that haze we subtracted, is actually moving ever so slightly. And you can see it shift from the bottom to the top of the movie. So we have to get rid of that. And we can see some trails that are left by the statistics of the images where the stars used to was. So all of that we can take care of by fitting a cubic polynomial to each pixel. Now you can see there's really something going on, and it's about as bright as what's left over from all this other stuff we threw away. Well, to get any farther, we have to use the image structure itself. We can use the Fourier transform, which is a mathematical method that I'm not going to talk about, but we can use it to isolate things that are moving at a certain range of speeds through the movie. When we do that, it gets rid of all this sort of background crud that's not moving very much. That gives us this. Now we're cooking with gas. That is the solar wind itself. And look at the scale, from 0 to 0.03. So we are a factor of 1,000 inside the dynamic range of the original movie. It's the same data. We've just stripped away layer upon layer to get to what we want. So we can resample back into the instrument coordinate system and merge with other batches of data and photometrically calibrate it, and then we get this. And so this is a movie of the solar wind propagating through the solar system on a scale of about an astronomical unit. You're seeing this faint haze of material with a density of about 10 atoms per milliliter. That's 50 atoms in a 50 atoms in a teaspoon, if you don't like SI units. 10 atoms per milliliter if you do. Very tenuous material, very close to nothing at all, but visible. And even though it's so tenuous that the atoms in it never encounter each other, they trade momentum through the magnetic field as they propagate. And that little bit of momentum trading means they act as a gas. They're a fluid traveling out at hypersonic rates through the solar system, sweeping over us. And you can see it. So with Punch, we'll do this routinely, and we'll fix a little bit. This old-timey movie look that you're seeing is because stereo had a mechanical shutter. Mechanical shutter varies by about 0.1% in exposure time, and that has a huge effect on the output. Also, there are little tiny nonlinearities in the detector that we couldn't correct. And that leads to this flashing wherever a star is crossing over the pixel grid. We can fix that. We have fixed it for Punch, so we won't have those problems. So we live inside a torrent of star stuff, material leaving our star, sweeping across the solar system at 1 to 4 million miles per hour, sweeping over our planet. With Punch, we're going to visualize it. We will help you see this material as it sweeps across the solar system and over us. It is in the sky right now. It's just too faint for you to see. If you come here to our website, you can get our data and find out about events and learn more about the mission. Thanks for your attention.
Thank you, Dr. DeForest. That was wonderful. At this point, we would like to open up the floor and those online for question and answer for you to talk to them.
Sure.
Go ahead. There's a mic over there. You'll have to.
The recent blackout, is that working? The recent blackout in Spain and Portugal, like about a week ago, I heard a rumor that might have been caused by a coronal mass emission, but I haven't heard anything since then. Is that true? It was a solar event?
I do not know for sure, but I think it's very plausible that that event happened during a geomagnetic storm, and we know that similar events have happened. The famous one is the Hydro-Quebec failure in 1989, 87, late 20th century. We've managed to avoid that in North America since then, largely by learning how to forecast space weather and modifying power trading. So I can't definitively say yes, but my informed intuition is that yes, it probably was related. Brad.
Yeah. Can Punch see incoming Carrington events with time enough to know that they will hit the Earth and to notify anybody?
Haha, that is a great question. Would Punch see a Carrington event in time to warn everyone? Punch is a scientific mission, not a forecasting mission. And so we have no particular requirement on the latency of our data. And in particular, our background subtracted science data arrive 2 weeks after we observe them, which is too late to forecast. However, that said, NOAA has asked us for forecasting quality data, and we are delivering it to them, or we will be delivering it to them. Those data are delivered on a best effort basis, so we're not allowing them to drive the mission characteristics. But we think we can get data to them from our coronagraph about 6 times daily, which means the average latency is between 2 and 4 hours, which is plenty of time to forecast such a thing. The wider field stuff has a longer latency because the wide field imagers only talk to the ground once per day. So we might or might not be able to track such an event across the solar system before it impacts the Earth. That's just the nature of the beast. If anybody wanted to, we have the capability to provide a forecast capability, but somebody would have to pony up and pay the ground station providers to give us more passes. Ron.
I've got a couple
Oh, I'm
questions.
sorry. Oh, go ahead, Ron, and then someone in the room. Yeah.
Okay. First of all, thank you for a fantastic presentation. That was very informative. Couple questions regarding maybe some of the mechanical bits on the spacecraft themselves. I'm curious about the station keeping, or what's being used for station keeping. Is it hydrazine or something else? I'll start with that question and go to one or two more after that.
All right. Well, your check's in the mail for asking that question. We use we use a novel booster system. We do need to station keep because the Earth isn't a perfect oblate sphere, and so everything drifts a little bit over time. The same rocket engine that stops us is exactly the right scale to help us just get little nudges to stay on station. What we do is we carry a half a liter of water on each spacecraft, and we electrolyze it about a half a milliliter at a time, and then burn the hydrogen and oxygen in a little pulse. So we get a little pulse jet. Our specific impulse is about 250, I think, 250 seconds. So it's not great, but it's perfect and it's non-toxic. Furthermore, it's not dangerous. Your body it doesn't run on sugar, right? It doesn't run on carbs. It runs on adenosine triphosphate, ATP. But your cells only keep a few seconds worth of ATP around at any given time, right? That's why cyanide works so fast. It interferes with that. And the reason for that is ATP has so much energy, it's explosive, right? You don't want to store that in your body. So same kind of thing with the rocket engines. So Ron, forgive me, I interrupted somebody in the room who was asking a question. Let's go back.
Go ahead with the room, and I'll ask again later, or another question later. Thank you.
My question is, what was the main decision that drove the 1 and 3 satellite configuration?
Aha. So why did we go for 1 and 3? We knew that we needed approximately 3 of the wide field imager, but the question really was whether to mount them all on a single probe and send it far away from the planet, or just mount them on multiple probes and spread them around the planet nearby. And the remarkable thing is that, who knew, mass production saves money. In this case, we were able to buy commercial subsystems for the spacecraft. So our attitude system, our thrusters, our radios, our electromagnets that allow us to torque the thing off of the Earth's magnetic field, the solar panels and the batteries, all that stuff we bought from commercial providers. People designed them as sort of generic devices. We made sure that they met our requirements, and then we integrated them into a spacecraft. That reduced costs enough that it was actually cheaper to build 4 spacecraft and keep them near the Earth than to build 1 spacecraft and send it out into deep space and then try to phone home all the time. So cost.
Anybody else? I have a question.
Yes.
How long is the Punch mission projected to last?
How long is it? That's a loaded question. We haven't lost funding yet. Our prime mission is 2 years. In 2 years, we think we can satisfy all of our original science goals. However, I will note that the orbit is stable for 25 years, and will be in this ideal observing configuration for at least 4 years. So we'll be able to collect at least some data as long as somebody wants to keep the lights on. Our belief is this is really going to change the way we see the solar system, not just scientifically, but in terms of space weather. A few of us in the room are old enough to remember a time when weather satellites were relatively new. Before weather satellites, if you wanted to track a hurricane, you had to put individual ground stations on the ground, which meant you had to sail ships out into the ocean at a time when you knew a tropical depression was forming. And then you would have really scanty images or really scanty data that would be radioed back from those ships, indicating wind speed and things like that. It's very hard to predict where a hurricane would form or land. Of course, now we're all used to looking on TV or on our computer, and you can see hurricanes forming in the ocean and moving, right? And there's a whole science to forecasting how they're going to evolve. I think this will do the same thing for space weather, that we will be able to track these storms in 3 dimensions with this instrument. And having done that, I think we as a species will not want to go back. As long as we need to forecast space weather, I think we'll see polarizing wide field imagers after punch.
Thank you.
All right, Ron.
Any more in the room? Online, Ron, I think you had a question?
Oh, I've got more. Yes. And it's a perfect segue from the last question. And it had to do with the polarization discussion. You mentioned that the polarizing is linear polarization. I'm curious if any work is done with circular polarization, looking at these things.
Quite a bit. The stray light, the scattered light from the corona isn't particularly circularly polarized. However, we use circular polarization to measure the magnetic field on the surface of the sun. In the presence of a magnetic field, for those who don't remember esoteric physics, a spectral line, which has a particular color, will split into a slightly bluish component and a slightly reddish component. And the degree of that split depends on the strength of the magnetic field where the line is being emitted. Furthermore, those two versions of the spectral line are circularly polarized. So if you point a spectrograph at the sun and you put a circular polarizer in front of it, you can flip the polarizer or flip it in and out and see the wavelength shift of a line, and that tells you how strong the magnetic field is, even though it's 100 million miles away. You can do it, for distant galaxies, scale it up to 100 million light years. So people do use circular polarization, but just not for this. It's not particularly useful for the corona.
Okay, well, on that subject of the magnetism, the shift toward red or blue, does the sense of the polarization change, left-hand versus right-hand polarization on either side?
For the Zeeman splitting, it does. For the scattering here, the light is polarized along a line that is perpendicular to a radius on the sky. So if you draw a radial line from the sun to a feature, the polarization is perpendicular to that. And it's for the same reason that polarized sunglasses work, right? If you have polarized sunglasses on, light that scatters off a horizontal surface will end up being polarized horizontally. So by emitting only vertical light, your sunglasses block out glare, which is light that's been reflected off a horizontal surface. So similar kind of thing. In the plane of scatter, the polarization is perpendicular to the plane of scatter. So I drew that triangle on the screen. The polarization is perpendicular to the screen in that case.
Very good. Thank you for that. One more question. You mentioned the data will be available starting in June. Will it be on the site that you've got listed on the screen there?
We're not distributing it directly from that site, but there will be a link to the archive from there. So we're distributing it directly from a NASA archive, just because they can handle the volume and we may not be able to. So instead of sending the images out to everybody who pings our web browser, our web server, we send it out once to a NASA center and then they fan it out to everybody.
Okay, very good. Thank you. Joe, I think there are a couple questions on the chat too.
Okay. You see any?
Oh, here, I've got the chat. Brad Schaefer asked, is the zodiacal light really as clumpy as shown in your picture? There is no zodiacal light in this picture. I'll go back. The zodiacal light is not especially clumpy. Let's see if I can find the image. Here's the final movie that I showed there. That's what the zodiacal light typically looks like. And it is not especially clumpy. That's what allows us to remove it. The corona and the solar wind are quite clumpy. They're so clumpy that when we made those low noise images of the outer corona, quite a ways back here, I'll pull it up. Here we go. This movie here, there is so much going on here. It's hard to see just if your eye isn't trained to it. And I didn't bring the enhanced movie, but there's so much irregularity coming out of the sun in all directions. We called it a riotous torrent rather than a series of ejecta. So the corona is amazingly clumpy. It's so clumpy that in fact this movie is consistent with all of it being the result of individual ejecta leaving the sun rather than having any smooth flow at all. It's also consistent with some smooth flow, so that doesn't rule it out. But it's remarkable that it's even consistent with no smooth flow at all, with everything being ejected.
So we have a few.
Go ahead.
Go ahead, Craig. Were you done with that?
I'm done.
Okay. So we have a few questions through chat. We have a question from Brad Schaefer.
Oh, that was the one I just answered.
Oh, I beg your pardon.
Pardon me.
David Grant says, speaking of ATP, could punch data help constrain Goldilocks zones?
It could, in the sense that it will help us learn more about how stellar coronae work. Right now, we don't actually know basic things like what's the physics that sets the interplanetary magnetic field. I've talked about field lines being dragged around, and there's a lot to that. There's an imaginary surface at the outside part of the corona. It's somewhere in this field of view, called the Alphane surface, and that's a locus, a region of space, where the outflow speed here exceeds the largest wave speed in the material, where the material goes from, in some sense, subsonic, we call it subalphanic, to superalphanic. An alphane wave is a mix. It's a wave it's like an electromagnetic wave, but with mass on it. So it travels at a speed much less than c. When these structures exceed the wave speed, they can no longer communicate their position back to the sun, right? If you leave the room right now, just walk out, all the air in the room will rearrange and fill the void where you were. And what tells the air where to go and how to fill that void is sound, right? The very same thing you're using to communicate with me right now, mediated by the network, is also used by air molecules to find the new equilibrium when objects move around the room. So when things move faster than the sound speed, all hell breaks loose, right? You get sonic booms and things like that, shock waves. But also, before a shock wave hits, nothing knows it's coming, right? You can see shock waves if you go to the beach, which is a long way for most of us who live in the Denver area. But a crashing ocean wave is a shock. And the water before that wave hits it has no idea that it's about to be hit. That's not the case for an ocean swell, right? The swell comes on gradually and water lifts up gradually. The same thing is true here, that if the waves can't propagate in toward the sun, then the information itself can't propagate through the medium. And so things that happen outside that invisible surface, where the wind is flowing outward fast enough, they cannot change the way the corona looks. I'm going somewhere with this, which is the corona out here is radial because the magnetic field in it is radial. And so field lines have been dragged out by features through leaving the sun, right? Like that one that just went by. They get dragged out through this Alphane surface. Once they go out, they are stuck. Nothing can retract that field line back down toward the sun. And so it becomes a source surface. The sun becomes essentially the magnet that's driving the magnetic field in interplanetary space. We do not know the physics that sets that equilibrium, that relates the field on the surface of the star to the field in interplanetary space. So you asked about the Goldilocks zone. One aspect of a Goldilocks zone is how active is a star and how strong is the interplanetary magnetic field. We don't actually understand yet the physics that controls that, which has to do with how magnetic field gets carried across that imaginary surface in the outer corona. The reason we don't understand it is we couldn't measure that locus until just recently. Parker Solar Probe has recently flown through that zone. If you look for Alfvén, ALFVEN surface on Google, you'll see all kinds of news items about Parker Solar Probe flying through the Alfvén surface. That's why we scientists care about it. And it bears directly on, will punch data help us constrain Goldilocks zones? Yes, by identifying the mechanisms that allow stars to control the magnetic field in their environment, and how active the interplanetary environment is around a star, our star. We'll learn more about exoplanets and exosystems. Sorry, I get excited about this. It's cool.
No, thanks. Yeah, that's great. A G star, right?
Exactly.
Yeah, I know. I think sometimes I wonder how this activity doesn't knock the planets out of their orbits. But when you say the faintness, you show the faintness of the waves coming at us. It's no wonder it doesn't knock us out. They're just affecting us. But we've done good. We've done well for so far. Yeah.
Exactly. All of this material, it is really surprising to think about, right? I mean, this material is much larger than the sun itself, right? The corona is extending all the way across the solar system, right? Filling and becoming the heliosphere. And yet the entire corona has about as much mass as Lake Michigan. Right? I mean, let that sink in, right? Lake Michigan is something you can go sail on, right? You can cross it. And the mass of the water in Lake Michigan is within a factor of 3 of the mass of the corona itself.
Yes.
Rick, had a question. You were showing earlier a couple of videos showing the transition of the streamlines from what looked like smooth flow to turbulent flow. Is there anything akin in this kind of analysis that's kind of like a Reynolds number that helps predict where that transition is?
There absolutely is. And in fact, the magic number you're seeking is something called the plasma beta. The Reynolds numbers are very high throughout the whole corona because you have strong shears, right? Each of these radial field bundles in the corona itself is like a straw, right? It's a tube that directs the material that's passing through it. And so you can support very high shears. Normally, Bernoulli forces would cause vortices to develop, something called the Helmholtz instability that breaks up jets of air, forms and causes turbulence. But the magnetic field, the same thing that makes sunspots form, prevents that instability from causing turbulence. It does it by preventing lateral flow. So as the field weakens, the beta parameter, which is in some sense the ratio between the energy contained in the magnetic field and the energy contained in the material itself, that ratio goes from a very low number, which means the magnetic field dominates the system, up to about unity. So out here where the cursor is now, the magnetic beta parameter, the plasma beta parameter, is crossing through unity. When it does, the dominant physics changes. Down here, it's the confinement from the magnetic field. Up here on the left, it's the desire of gases to become turbulent. And so when that suppression fades out, the turbulence turns on.
Thanks.
Any more questions online or in the room?
Well, it's such a pleasure to talk with everybody. Thank you all for coming tonight and for tolerating a Zoom speaker. I really wish I could be there in person, but I'm glad to be able to talk with you at least virtually.
Thank you, Dr. DeForest. That was very good, very good.